Hey friends. So we are going to be going through standing wave notes, which is on page 14 through 16 of your packet. So remote students, you should have this up. You can side by side with Notability in the video or Zoom, and then in-person students, you should have your physical paper packet or they're in the room at one of the front tables. So, a standing wave is not really anything new. It's just a cool type of wave. So we'll talk about what they are and we'll look at some examples. So, the first thing that you need to know about standing waves, and this is written in your packet already for you, so nothing to copy down here. It's basically a ton of waves happening where there's an incident wave, so you make a wave, but then there's a wave that is also reflecting and moving backwards down like a slinky. And when they do this just right, you get these giant waves. So watch for this pattern to emerge in the video. So there the pattern is. The wave became a lot bigger. And this is a principle of interference. So if you look at our first page, there's constructive interference and there's destructive interference in your packet. And so I'm going to show you what constructive interference actually looks like. There's a picture here, but I feel like sometimes the picture is kind of confusing. It's better to watch it on video. So we've got these two waves. And they interfere with each other, right? They cross over each other. So we're going to go through this step by step. They're going towards each other. And pay attention to, did you see how it became the amplitude became a lot bigger when they interfered with each other? That's constructive interference. So it's when two waves interfere with each other, they like pass through each other, and they make a really big amplitude. So that's what's happening with standing waves is those waves are interfering with each other. They're constructively, and that's why we see the wave get a lot bigger when we see that standing wave. Now, destructive interference is also important for standing waves because that's the places on the slinky or on the wave that look like they're not moving. So if we go back in our video and watch this again, you see how like this location, there's like places that almost look like they're not moving. Like right here, it kind of looks like it's not moving. So that's complete destructive interference. And that's what happens here. We got two waves. Now, one of the waves is below the axis. And we'll do that in slow motion again. So they go towards each other, towards each other, towards each other. And because the right wave is negative, it's below the x-axis, it removes amplitude for from the one on top. So it's almost like the bottom one is like taking a bite out of the top one, and we're left with less. Okay, so a standing wave is a pattern formed. So this is page 15, sorry, not page 14. And it's a bunch of these waves. So there's like the incident, there's the reflected wave, and these waves add up to make a really big amplitude. So this amplitude of this resulting standing wave is 4 times greater than this amplitude of one of the individual waves, because there's 4 of them. Okay, now a standing wave, we got to talk about the parts of the wave. So this is a video that might help a little bit with figuring out how this happens. So we've got a wave. This is like super slow motion from what happens like when we make a standing wave on a slinky in the classroom. But see, the wave is approaching that wall and it's going to reflect. So this blue wave is the reflected wave. And now look at this the black dots. Do you see how it's constructively interfering and destructively interfering? So the places where the black wave is the biggest is when the red and the blue, so remember the red is the incident wave, it's like the first wave, and blue is the reflected wave. It's when they're right on top of each other so they can sum together to give that giant amplitude. And notice the ends, those are called the nodes, and those are complete destructive interference. So those particles are never displaced because they always have this perfect positive negative that's canceling out with the red and the blue wave. Okay, so let's label. Most of this is labeled already for you on page 15, but the crests are still the same, the troughs are still the same. The nodes are places with 0 amplitude. So I always remember it by thinking node means none or nada or nothing. So nodes mean no amplitude. Antinodes means the opposite. So if you can remember node means nothing, then you can remember that antinode means the opposite, which is some amplitude. So antinodes are anywhere where there's maximum amplitude. Nodes never are displaced, so they just stay there. And notice there's this solid line and the dotted line. So the solid line reflects the actual wave, like the incident wave, and the reflected wave is shown with the dotted line. So this is all already copied down for you. Nothing really new except for nodes and antinodes. Okay, so this is a cool video of a standing wave being created and how you can see the nodes a little bit better. So there's the reflection, right? You can clearly see there's the incident, the reflection. Now he's going to try to make one standing wave. So he's labeling node, node, antinode. So this basically looks like a half circle or like one bump, which is half a wave. Try to spot the node. So here's the node right in the middle. We have one full wavelength. Okay, so here you can see it's one bump, two bumps, three bumps, so that means it's like a wave and a half. That's one more half, so that's two waves. Okay, so you get the point, kind of. All right, so we're going to practice now counting standing waves. So this is on page 16. Page 16. And what I would like for you to do now is I would like for you to count the number of waves shown in this diagram. So how many waves do you see here? Write down your guess. How many waves do you see here? Write down your guess. How many waves do you see here? Write down your guess. And when I say waves, remember I mean wavelength. I mean wavelength. Okay, so you should have your 3 guesses down. And now I'm going to show you what the 3 answers are. Half a wave. Because remember, one full positive bump and one full negative bump is 1 wave. So this is 1 wave. And then this one has 1 more bump, so it's 1.5. One way that sometimes students like to do this is they like to count the number of bumps and divide by 2. So if you see like 1 bubble, or bumps or bubble, whatever you want to call it, that would be 1 divided by 2 waves. If I see 2, that's 2 divided by 2, that's 1 wave. If I see 3, that's 3 divided by 2, that's 1.5. So sometimes students like to do it that way when you're counting waves. All right, now let's do this one. This one can be kind of tricky, but I think you can get it. I think you can get it. Think about what this looks like. Is that 1 bubble? 1 wave bubble? Is it a half wave bubble? What about this side? So write down your guess here. Do the same thing here. Focus on either the solid line or the dotted line. Same thing here. Focus on either the solid line or the dotted line. Okay. Half. So the way that I like to think about this is the distance from a crest to a trough is going to be half a wave, right? Because distance from crest to crest is 1 wavelength, and so distance from crest to trough is a half. The other way you could think about it is this is a half bubble, so is this. 2 half bubbles make 1 whole bubble. 1 divided by 2, that's how many waves I have. This is from crest to crest. Here's a crest, here's a trough, here's a crest. That's 1 wavelength. Crest, trough, crest, that's 1 wavelength plus a half. The other way is this is half plus 1 plus 2 plus another half. That's 3 bubbles total divided by 2, 3.5. Okay, so let's do another one. This one, instead of having open ends and open ends, we're going to have a closed end and an open end. So we give some examples like an oboe or a horn or clarinet. But this time, maybe use the bubble method, focus on one of the lines, whether it be the solid one or the dotted one, and count your waves, make a guess. So guess, and then we can always correct it, but I do want you to try to count them on your own. And be careful with this one, it's a little tricky. All right, first one, did you fall for the trick? It is not half a wave. That's the most common wrong answer. It is half of a wave, so a quarter. So we've got half of a bubble, which means half divided by 2 is 1/4. Okay, now what about this one? We've got 1.5 bubbles, so that means 3/4, right? It's almost a full wave. If this went all the way to equilibrium, that zero displacement place, then we would have a full wave. So it's a little bit less than a full wave, but it's not half a wave either. And then this one, you're maybe seeing the pattern, 1/4, 3/4, 5/4, right? Add another half, so 1.25. Sorry, I think I was covering that. 1.25. And again, 1, 2.5, 2.5 divided by 2. Okay, so here's the exciting thing, and I know I've been promising this third equation. It's coming in. This is the last equation we need for LT5 in this unit. If we know how many waves there are in a string, and we know how long the string is, we know what the wavelength is. So this is one wave, and let's say it's 3.5 meters. Well, if we have one wave on a string that is 3.5 meters long, that means a wavelength is 3.5 meters. Right? So this is our new equation. Number of waves times the wavelength gives us the length. Number of waves times the wavelength gives us the length. Or it's written in the other form on page 17 of your packet. Wavelength is equal to length divided by number of wavelengths. So if the length is 3.5 meters, and we have one wave, in this total length, that means our lambda, wavelength, is 3.5 meters. Okay, let's try some more. So you try to count these 4 waves. So count how many wavelengths are there in 1, 2, 3, and 4. You try. I'll give you 1 minute. Sometimes students like to do the tracing method where they count while they trace. Some students like to count the bubbles and then divide by 2. You got to pick whichever way you like best and you find you are most successful with. Okay, this tree one, we've got 1, 2, 3, 4, 5, 6 bubbles, which means 3 waves. Or if you're tracing, that means 1, 2, 3. Just stick with one of the lines. This one is 1.5. Or if you count bubbles, 1, 2, 3 divided by 2, 1.5. This one is not quite a half, so it's a quarter, 0.25. This one is from crest to trough, which is half of a wave. Okay, so now let's use this equation. Let's say each of these strings, and this is not in your packet, this is just for us to practice with and see if you can follow along with the math in this equation setup. So I've got my equation up here, and I know the length is 3.5 meters of the whole string. So every single one of these has a length of 3.5 meters. I count one wave in this first picture, so that means my wavelength is 3.5 meters, right? That one's pretty easy. Number of waves, 1 times something equals 3.5. We already did that one. Okay, now what about this one? This is half a wave, so that means half of a wavelength times wavelength gives me 3.5. So 3.5 times 2 is the same thing. This one, we've got 3.5 waves. So that would be 3.5 meters divided by, or sorry, not 3.5, 1.5. 3.5 meters divided by 1.5, or multiplied by the reciprocal. Instead of 3.5 and 3 halves, it'd be 2/3. And then this one, we've got 1, 2, 3, 4, 5 wave bubbles, which means 5.5 waves. So that means our wavelength will be 3.5 meters times 2/5, or 5 halves times wavelength equals 3.5. Solve for wavelength. Okay, now let's do it the reverse way, which I think is maybe a little bit easier, where you're given the wavelength and you need to figure out what the length of the string is. So here we have a picture and the wavelength is 2 meters. So we have one wave, which means our length has to be the full wavelength. So one wave, 2 meters equals L, 2 meters. This one we've got half a wave. So the number of waves is 1/2 times the wavelength, which is 2, gives us a length of 1 meter. This one, we've got 1, 2, 3 waves, or 3 bubbles, so that's 1.5 waves. 2 meters times 1.5 is 3 meters. So again, it's the wavelength times the number of waves, which gives you 3 meters. Here we've got 1, 2, 3, 4, 5.5 waves. So 2.5 waves, or 5 halves of a wave, 2.5 waves. So that's 2 meters times 2.5, which is 5 meters. Okay. So let's use this picture as an example. So do this one under number 1 on page 17. If the wavelength is 1.2 meters, the length of the rope is what? So let's say the wavelength is 1.2 meters. We know how many wavelengths there are. We already did that. So under number 1 on page 17, you try this one. I'll give you 30 seconds. Make sure you write the equation. So number of waves times wavelength gives you L. There are 3 waves, we counted them, times 1.2, which would be 3.6 meters. Okay, let's try this one. So this is under number 2. Let's say the length is 0.3 meters. How many waves are there? 1/4. So we've got 1/4 times the wavelength gives us 0.3 meters. If you do the math, that's 1.2 meters. The whole wavelength would be 4 times bigger than the actual length. All right, so that is it for notes. You are going to submit now on the Canvas assignment called Standing Waves Notes. You're going to submit your notes for these pages to show me that you did them. And then with your extra time, you are going to work in your breakout rooms on Standing Waves LT5 practice. So that's pages 18, 19, and 20 in your packet. You have a formative on Monday, which has LT5A, LT5B, and LT6 on it. So this is some good LT5 practice, since we've mostly been focusing on LT6 this week. All right, I will see you all on Monday, and let me know if you have any questions.